First, I will present another, probably more or less speculative application of this idea of gauge invariance, namely now applied to the field of computational vision. And in computational vision, you probably know that edge detection is a very important issue in computational vision, because in order to process images, one of the first steps that has to be carried out is edge detection. And for grayscale pictures like this famous lithography of MC Esker, for such grayscale pictures, there are very well-established algorithms for that. One of them is the Kenny algorithm, for example. Another one would go as follows. So for such a grayscale picture, we can prescribe this picture simply by a scalar field. So a quantity, a real number, assigned to all the points in the plane. So we assume that the image has a rectangular form corresponding to an interval 0 to a times 0 to b. So it's a planar or a two-dimensional scalar field. And then the algorithm, or some of the algorithms, work as follows. So if we can find an edge, so a parameterized contour in this field, a necessary condition for that would be that the Laplacian applied to the field following the edge should be 0. So find the zeros of the Laplacian, and then you can detect the edges. And if we do this for this picture here, this is part of the MATLAB environment, quite straightforward. You can see that the edges are nicely detected using the Laplacian filter here. How does this relate to gauge theory? Well, it does, namely in the sense as gauge theory is discussed in classical, or of course also in quantum electrodynamics. Namely, we can make a local gauge transformation of the scalar field by simply adding some other space-dependent function to this. And in that case, when this scalar field is also a solution of the Laplace equation, we speak about harmonic functions, then of course the solutions of the edge detection algorithm do not change. So here what I have done is I have superimposed to this grayscale image one particular solution of the Laplace equation, which is a harmonic function. Here you see some regions become darker, some regions become brighter. So it's a kind of spatial oscillation you can imagine. And then applying the edge detection filter again gives an invariant picture. And as I said, for grayscale images, this is straightforward. But now you can think, how can we apply what we have learned during this course? And probably you know that there is another application of gauge theory in elementary physics, which is called the standard model. And there you probably know there's one important branch within this theory, which is called quantum chromodynamics. And this simply metaphorically says that these particles, the quarks and the gluons, appear in different colors. And the reason for this is that you assume an internal symmetry group, which is SU3 in that case, and then you can develop the entire formalism of gauge invariance and gauge theory in order to describe these fields. And one possible application could be now to look not at metaphorically colored elementary particles, but simply to look at real colored images. And then, of course, we need, for example, a color space of 3 colors, of 3 base colors, for example, red, green, and blue, which you know from an old-fashioned TV screen. And then probably we can further develop such algorithms for edge detection, probably, that could be described by these internal symmetries. Okay. Now we need some more definitions again. And as before, I will illustrate, or I will motivate these new definitions again by looking at classical dynamical systems again. And what I have already mentioned is that we have the phase space of a classical dynamical system. And if you look at probability distributions over the phase space, then we get something like an epistemic description of the system. So we have to distinguish between the points in phase space, which give rise to the ontological description, and now we look at probability distributions, or likewise, we can look for their essential support, and then we identify regions in phase space or subsets of phase space. And I have already mentioned they could be called macrostates, and I will go into further detail today why they should be called, or why they could be called macrostates. And now we have to look how macrostates are related to observables in the algebraic pictures, So, of course, I have already told you that a classical observable is a real valued function from the phase space to the real number. And the measurement result that we obtain when the system is in one particular microstate is simply the image of this microstate of this point in phase space to the real number axis. In case of a probability distribution, things look somewhat different, because such a macrostate, probability distribution over phase space, becomes also represented by a probability distribution over the observable values, in that case, for example, Gaussian. And then we cannot say that the system is, or the system produces exactly one particular value of the observable. But instead, we can say that the system will produce the observable on average. And therefore, we have to describe expectation values in this framework. And this leads now to the next important concept, and this is the concept of a state. Of course, I have talked about states all the time when we were looking at the pioneer quantum mechanics, because there we know states are vectors in the Hilbert space, or states correspond to density operators over the Hilbert space. But now we can make this concept even more precise. So what is a state in a mathematical sense? We have to look at the dual space of the C-star algebra, which is, of course, the space of the star homomorphisms from the algebra into the complex numbers. And this dual space becomes a Banach space by introducing a norm in this way, that we consider a map rho from the algebra into the complex numbers. Then, of course, we can take simply the modulus of that complex number. We normalize this by the norm of the element of the algebra. Because we have a C-star algebra, there is this uniform topology. Then we take the supremum over all elements of the algebra, and this is the norm of the state. So in that sense, we can equip our the dual space of an algebra with a norm, and of course we can make the norm completion of that, so the dual space becomes a Banach space. Now we call such a linear form, or such a linear functional from the dual space of the algebra, we call it normalized, if the norm can be set to 1, of course. And more, even more interesting is that we can say that such a linear form of the dual space can be called positive if the norm, if the state evaluated at the product of the adjoint of some algebra element with the algebra element is larger or equal than 0. And now we only consider a subset of the dual space of the algebra, namely only the positive and normalized linear functionals, and these are called the states over the algebra. So we don't have the entire dual space of the algebra as admissible states, but first of all only the positive cone within this dual space, and then of course only the normalized elements are called states over the algebra. Well, let us look for another example again, and my first example is again the one that we have discussed all the times for a classical dynamical system. So here we have again a commutative C-star algebra, which was essentially this function space of continuous complex values functions over probably the n-dimensional hypercube again. And now what are the states? Well, the states are expectation value functions, as I have already explained in the initial motivation. The states evaluate the elements of an observable by mapping an observable to a complex number, or of course to a real number, in the case of having a self-adjoint element. And the result of this evaluation gives the statistical expectation value. So here for a classical system, we apply this state functional rho to an observable f, which is a continuous complex value function. And this can be expressed by taking an integral over all the arguments f of x multiplied by a probability density function. So now we are considering measures. And then, of course, we know that measures under some further assumptions can be described by probability densities. And for the algebra of continuous functions, we know that the probability density functions must be simply the measurable functions over the space. And therefore, the dual space of the space of continuous functions over our phase space is exactly the space of all the probability density functions, which is the space of the back measurable functions over the phase space. And by this definition here, we can assign to each element of the algebra the expectation value over phase space by multiplying the function as an element of the algebra by such a probability density. This gives us an expectation value function and therefore a state in a classical dynamical system. Well, here's an example, and sometimes one always has to realize that even mathematical physics is full of metaphors. And if you know, or if you are familiar with preparing a sauce hollandaise, you know that sauce hollandaise can be only prepared by very small energy exchange with its environment. And so you are using heat bath. And now in physics and in mathematical physics, a heat bath is nothing more than a metaphor for exactly the case of an open system that is weakly coupled to its environment. Weakly coupling now means there is no exchange of matter because all the particles stay within the preparation of sauce hollandaise. But there is a small energy exchange with the environment. And under these assumptions, an open system weakly coupled to its environment, you can make this standard assumption that I want to maximize the entropy under the constraint that the average of the energy should be hold constant. And in that case, you can immediately derive the so-called Gibbs density operator. So you have a canonical ensemble described by this Gibbsian density operator, which is simply the Hamiltonian of the system, so the energy operator of the system multiplied by a parameter, which turns out to be related to inverse temperature. So here we have the Boltzmann constant, and 1 over Boltzmann constant times temperature is this parameter. And then here, of course, we have a normalization term, which is given as a partition function, namely the trace of the exponential of the Hamiltonian times inverse temperature. Well, in thermodynamics, this is all very known that exactly this expression here maximizes the entropy under the constraint that the average entropy, that the average energy should be hold constant. And this exactly describes such an Gibbsian ensemble, namely an open thermal system that is weakly covered with environment, or in other words, a system in a heat bath. Here's another example, namely again talking about qubits and quantum spins. The states of the Pauli spin algebra. Again, the states are elements of the dual space of the algebra, mapping elements of the algebra into complex numbers. And the states of the Pauli spin algebra are now given as these density matrices. And you see this is simply a kind of linear combination of the 3 Pauli matrices together with the unit matrix. And then we can evaluate a state in an observable. So the state functional applied to the observable is then again given by what we have learned in the traditional picture of quantum theory as the trace of the density operator times the observable. And now we have a real parameter space. X, Y, and Z are real numbers, and they are constrained by the condition that the square of their sum, the sum of the squares should be smaller or equal than 1. And this gives rise to another, so to say, to another illustration, namely what is called the block sphere for such a qubit system. So we can describe a 3-dimensional parameter space for the 3 parameters of the density matrix. And then you see that the spin up state and the spin down state correspond to the poles of the sphere, and any other state corresponds either to a point at the surface of the sphere or to a point in the interior of the sphere. And interestingly, now we can make another observation that the state space of such a C-star algebraic system is a convex set. And the pure states, what we have called pure states in the framework of pioneer quantum mechanics, namely vectors in the Hilbert space, they are exactly the extremal points. So here the points on the surface of the sphere. And the non-pure states sometimes are called mixed points or mixed states. They are in the interior of the block sphere. But as now again Hans Primas mentioned many times, that in a quantum system, a decomposition of a non-pure state into a convex combination of pure states is not unique, because here in the block sphere we can make any kind of rotation in order to describe the same non-pure state by different parameter values given extremal points for a convex combination. The thing is completely different in a classical system, because the states in a classical system are also extremal points, or the states in the classical system are also elements of a convex set. And the pure states are extremal points, but in a classical system, the state space is always a simplex. And here we can uniquely identify the extremal points by the vertices of the simplex. And therefore, it makes sense to speak a mixed state in a classical system, but it does not make that much sense to speak about a mixed state in a quantum system because there is no unique mixture given. But of course, in the literature, you always find this distinction for both kinds of systems. So pure states are the extremal points in this convex set, and non-pure states are often called mixed states in both kinds of systems. They're either quantum or classical.
Sorry.
Yeah.
Why doesn't it make sense to speak of mixed states just because there's no unique decomposition of those?
Yeah, while the concept somehow alludes or uses the assumption that this mixture should be unique.
I don't see why. I mean, a mixed state is defined and through its density matrix, and there are several decompositions into pure states, or infinitely many.
Exactly, infinitely many, yes. Yeah, so maybe it's just a matter of taste. No, okay. Yeah. I think it's a matter of taste, and if you like, you can talk about mixed states here as well. But of course, as I said, for a classical system, this mixture is unique. Okay. Some further notions that we need to discuss. You remember that we can define Bayesian conditionalization for a probability measure by computing conditional probabilities. The same can be applied to quantum systems, to quantum states. And this means basically we assume that there's a state in the dual space of an algebra, and that be another element of the algebra. And then we talk about the modification of a state. And this is defined by the quantum analog, so to say, of the Bayesian conditionalization rule. So we evaluate the state at B adjoint times A times B, and normalize this by the evaluation of the state in B adjoint and B. And this gives rise to, so to say, a conditional probability, which is a new state, rho B, evaluated in the observable A. And so given one state, we can introduce many different other states by this conditionalization rule. And this is called a modification of the state. And now we can further restrict the state space from the set of positive normalized states in the dual space of the algebra to all the states that can be generated by this kind of conditionalization, by modification. And this set, so actually a convex and norm-complete set of states over a C-star algebra is called a folium, if it is closed with respect to state modifications. So all the states that can be generated out of one single state lie within the folium of this given state. And then additionally, we talk about the normal folium of a state, and this is given by the norm completion of all convex linear combinations of modifications of the given state. So here again, we compute some kind of mixture with partition of the unity. And here we produce a number of modifications of the given state. And if these elements, these convex linear combinations are all contained in our subset of states, then we talk about the normal folium of a state. Then one can introduce the notion of stability. So given a C-star algebra and its automorphism group, remember the automorphism group of an algebra is the set of linear transformations over the algebra, mapping one algebra element to another algebra element, and these automorphisms can be composed, of course, by functional composition. And now let us consider state in the folium of the algebra, and then we define the dual of an automorphism by defining its action over the state space. So here's the definition. Instead of evaluating the state in the transformation of the algebra element A under the automorphism alpha, we evaluate the dual automorphism in the state space and apply that to the element of the algebra. And now we say that the folium of states should be called stable under the automorphisms of the algebra if we have exactly this invariance property, that the dual automorphisms applied to the folium should not leave the folium for all automorphisms of the algebra. And now we are almost prepared to introduce the probably most important notion of the two-day session, so this is quantum dynamical systems. So what is a quantum dynamical system? A quantum dynamical system is a triple consisting of a C-star algebra, the folium of states, and the representation of the automorphism group. Again, A is the C-star algebra, F is the folium, and alpha is now meant to be a representation of the real number field, which is of course a group, a commutative group. So a representation of the real number group into the automorphism group of the algebra in such a way that the folium is stable under the actions of the automorphism group. And to be more precise, a C-star dynamical system is then a quantum dynamical system given as this triple of the algebra, the folium of states, and a representation of the automorphism group from the real numbers. If F contains all the states of the algebra, and if the automorphism group, now parameterized by these real numbers here, is additionally uniformly continuous in the algebra for all times of the real numbers.
F
Yeah.
is a subgroup of subset of U star, no? Or
Which one?
F is a subset of
A star, yes, precisely. The folium is a subset of the dual space of the algebra. Precisely. Well, let me make some further remarks on this point. Of course, in general, one considers a representation, a group representation of the real numbers, which corresponds to invertible, because each real number has a negative inverse element with respect to addition, which is a negative real number, of course. So we are considering an invertible, and therefore, of course, a deterministic continuous dynamical system by making this condition here. But of course, you can also study other kinds of quantum dynamical systems. So for example, you can consider a representation of the integer numbers into the automorphism group. And this would lead to a time discrete quantum dynamical systems. And of course, instead of allowing for group representations, where every element has an inverse element, and therefore the dynamics should be invertible and therefore deterministic, we can also consider semi-group representations. So for example, a representation of the natural numbers into the automorphism group. And this would be required for the description of non-deterministic, namely, for example, irreversible dynamics. And everything like you want can be introduced, so to say, in this algebraic framework of quantum dynamical systems. So, but now let us consider the two most important examples. So what is a classical dynamical system? And many times before I gave you this mathematical description, the classical dynamical system is given by a phase space and a flow map, which is parameterized by the real numbers. Now we can obtain such a classical dynamic system in its conventional notation, in phase space and flow map, by the Gelfand-Neumann representation theorem as such a triple comprising an algebra, volume, as a subset of the dual space of the algebra, and a representation of the automorphism group in the following way. Well, of course, for a classical dynamic system, we look at this abelian C-star algebra. We know that there are no other abelian C-star algebras than the function spaces of continuous complex values functions over some compact or locally compact, at least some topological space X, which we call a phase space. In that sense, we already obtained a phase space used in this, introduced in this description here. And of course, now the observables are simply the real value, namely the self-adjoint elements of the algebra. The state space, so what we have defined as a state before, was as an expectation value functional, and these expectation value functionals should be in this volume of the as a part of the dual space. And we know that we can evaluate expectation values pointwise in the microstates of the phase space by introducing the Dirac measures. So the Dirac measure centered in X is a measure, if you remember to our discussion of measurement theory. So I will use the blackboard for a moment. So the Dirac measure is, of course, takes as an element a set from a Borel algebra, and then we know this is 0 or 1, either if X is not contained in the set or if X is contained in the set. This is called the Dirac measure, and this gives a very simple kind of probability measure here. And by introducing the Dirac measures, we can identify expectation value functionals with the individual microstates in phase space. And finally, this is straightforward. We look at the automorphism group, at the representation of the real numbers in the automorphism group, takes the dual automorphisms, which are evaluated in the states instead of in the algebra, and this defines the flow of the classical dynamical system. In that sense, you can derive classical dynamical systems from the algebraic framework simply by means of the Gelfand-Neumann representation theorem. Here's the other example, namely how to describe a pioneer quantum dynamical system. And now, of course, this is obtained by the other theorem, namely the Gelfand-Neumann-Siegel representation theorem. Again, starting with such a triple of a C-star algebra, a volume of states, and a representation of the automorphism group. We know that we have to look at a non-commutative C-star algebra, and then we know such a non-commutative C-star algebra should be isomorphic to the space of bounded operators on a Hilbert space, or it should be at least a subset of this. And of course, the observables are again the self-adjoint operators within this set of this space of bounded operators. And now we look at the state space. The state space is again given by the expectation value functionals in the volume of the algebra. And of course, as far as we are looking at pure states only, these are simply given as the normalized Hilbert space vectors. So we have a Hilbert space, we can identify the pure states by vectors in the Hilbert space, and then of course we have exactly this representation of the state. And this we know, this is the expectation value of an observable A in a state psi in the Hilbert space. And this gives rise, we can say, to a state in our formula, in the sense of our formal definition. To each vector in the Hilbert space, we can assign one state given by psi, evaluating elements of the algebra. And finally, we have to talk about dynamics. And as long as we are in the Heisenberg picture, we describe the dynamics of observables and not of states. And then we know that we can implement these automorphisms unitarily in the Hilbert space simply by making this kind of similarity transformation where K is so to say a dimensionless or a kind of Hamilton operator where we the Planck action constant here. So this gives the Heisenberg picture of quantum mechanics. And then, of course, you can make another transformation from this description here to the Schrödinger picture, where the states become time dependent and the observable remain constant, which is straightforward. And then immediately you can derive the Schrödinger equation from this point here. And that's the way how the algebraic framework gives us the picture of traditional quantum physics.
Peter, what about the case where you'd have a system that has both a quantum and classical aspects? How would you represent that?
This is essentially the same as here, but then of course what we have already discussed in the algebra, there is a non-trivial center, and these are the classical observables. And they can, of course, these classical observables commute with all the other observables of the algebra. And therefore, what we have written down on the blackboard some days ago, that the classical, the states evaluated over the classical observables are always dispersion-free. And therefore, they can be identified, so to say, with single points in the corresponding phase space. Okay, now we are ready to come to the next important notion, and we were talking about C-star algebras last days. Now we introduce another important concept, that's of a W-star algebra. And in the literature, you will often find the same term as von Neumann algebra. This is essentially the same. So let us look at a C-star algebra. Call it M. If this C-star algebra possesses a Banach space as a pre-dual, it is called a W-star algebra. What does this mean? It means the following. The W-star algebra is the dual space of a Banach space. So this is the definition that we have here. So there is a Banach space, and its dual gives us the algebra, and that means we say that the Banach space is the pre-dual of the algebra, because the dual of this space produces the algebra. Why is this important? Because now the topology, and we have discussed this also already, the Banach space induces a weak topology. And this applies now also to the algebra. And here's for you an illustrative example, talking about topology again. The norm of the pre-dual induces a weak topology in the W-star algebra, and therefore one talks about W alluding to weak. And this leads to emergent concepts of convergence of function series, namely, for example, the convergence in quadratic mean. What does this mean? For C-star algebras, we had a uniform topology that was induced by the supremum norm or by the maximum norm. And if you remember, my example was the convergence of polynomials against the sine function, and this was uniform convergence. So for a certain order of polynomials, they are all captured by a uniform stripe around the sine function. This is completely different here in this case, where I'm now trying to approximate a rectangle function by a sequence of sine functions, namely by Fourier series. And then in order to discuss convergence of Fourier series, we cannot talk about uniform convergence at all. We have to define convergence in quadratic mean, which means that we evaluate the norm of the function defined by the scalar product in the Hilbert space, or correspondingly by the corresponding norm in the Banach space. And this gives rise to the convergence of a trigonometric polynomial. And here we approximate actually the sine function giving the sign of the argument here. And that here you see also in the picture, there is no uniform convergence at all. So quite often this trigonometric polynomials escape here from the stripe of uniform convergence. And it becomes even worse when we get a higher order here in the trigonometric polynomial. And therefore, we have a very weak notion of convergence here in comparison to the uniform convergence that we have discussed in the framework of C-star algebras. And another important point here also in this definition, now you see here we are evaluating integrals, and that means we have to talk about measure spaces. And this is a quite interesting issue that usually one says that C-star algebras are connecting algebraic properties with topology, and W-star algebras are connecting algebraic properties with measures, with measure theory. Another important thing is that having started with an original C-star algebra and computing or making the construction of a W-star algebra, we can canonically embed the original C-star algebra in the extended W-star algebra. So how does this work? So let us start with the C-star algebra. Then we look at the state space, which is the dual space of the C-star algebra. And now let us simply look at the dual of the dual, which is called the bidual. So we start with the algebra. We take the states, which is the space of linear functionals mapping algebra elements into complex numbers. This is the dual space. And then again, which is of course a vector space again and a Banach space. And then we can of course make repeat this construction looking at the dual space of the state space, which is the bidual of the original algebra. And this bidual contains now linear functionals mapping states onto complex numbers. And in this bidual, we can canonically embed the original C-star algebra simply by this rule here. So here we are in the algebra. We evaluate an element in the algebra by means of the state. And this gives us a complex number. But equivalently, we can look at the state and evaluate the state by one of its linear functionals, which also gives a complex number. And this is the rule to identify elements of the original algebra with elements of the bidual of the algebra. And this is the so-called canonical embedding. And interestingly, this construction here, this is, so to say, at the core of this Gale-van-Neumark theorem in order to prove that all the abelian C-star algebras are essentially isomorphic to function spaces over topological spaces as a phase space. Because now here, in this setting here, we can identify the states with microstates with points in a phase space. That's it. Well, here's another example again. Look at the commutative C-star algebra of the continuous complex weight functions over an n-dimensional hypercube. How do we construct the W star algebra? Well, the W star algebra is called the space of the essentially bounded functions with respect to the Lebesgue measure. How does this work? In the following sense. First, we start with our function space of continuous valued, of continuous complex valued function. Taking its dual space, we know the dual space contains or is described by the probability density functions. And this is the space of measurable functions, the Lebesgue measurable functions over the phase space. And now compute the bidual of the original algebra of continuous functions, which is the dual of the measurable functions. And this involves some function analysis. This proof, of course, this cannot be carried out in the algebraic framework alone. But then you have to realize this is exactly the space of the essentially bounded function systems that do the Lebesgue measure. And in that sense, here you see, if you remember, the situation in linear algebra, where we were looking at finite dimensional vector spaces, we already see that the finite dimensional vector space is isomorphic to its dual space. And therefore, it's also isomorphic to its bidual space, and nothing changes. Now, I can take a CN and compute, start with CN, and then I take CN star, which is still isomorphic to CN, and then I can take CN double star, which is isomorphic to CN, and of course, it's still isomorphic to CN. The situation is completely different in the framework of functional analysis when we are looking at these function spaces here. The algebra of continuous functions can be canonically embedded into the algebra of essentially bounded functions, but that space is much larger than the space of continuous functions. And I give you examples for this as well. But first, let us try to get an intuition what is meant by this construction of a bidual. And this gives rise to a very important concept now, which we call macroscopic observables. So consider a classical dynamical system again. So we have a phase space, a topological space, and we identify the Dirac measures as expectation value functions with the individual points, the microstates and phase space. Now, an observable in a C-star algebra maps the microstates to some measurement results, which are real numbers. In general, the states are not simply Dirac measures, but the states are expectation value functionals given by some density functions, probability density functions over phase space. And so this is reflected by a corresponding probability density function over the measurement results. And this function can be now further mapped to another real number. And here we are in the dual space of the algebra, and here we are now in the bidual space of the algebra, namely in the dual space of the state space. And this construction here, so the elements of the bidual of the algebra that we can call under certain conditions that we call the macroscopic observables. So we have here the intrinsic observables, one could say, evaluating the individual states in the phase space. And here we have the macroscopic observables evaluating probability distributions over phase space. This leads to the concept of what we can call macroscopic, or in some of my own work, I call it this epistemic equivalence. So we can now define what is meant by macroscopic equivalence. So let us consider again the n-dimensional hypercube as some compact Hausdorff space of microstates of an C-star algebra, namely the algebra of continuous complex valued functions over the phase space. So then we know the state space of this algebra is the space of measurable functions, and the bidual is given as the space of essentially bounded functions. And this is the associated W star algebra. And now my claim is that the W star algebra contains, among others, these macroscopic observables. And now we can evaluate the elements, of the W star algebra in two different states. So these are two probability distributions over the phase space. And we call these two states macroscopically equivalent, still in the classical framework now, when there's a macroscopic observable, namely a bounded and essentially bounded observable, such that the value of this macroscopic observable is the same in two states. And in that sense, macroscopic observables define an equivalence relation over the state space. And this leads, of course, you know, an equivalence relation always leads to a partition. And the elements of such a partition then are called macrostates. So now we say a class of macroscopically equivalent states, namely given by probability densities, with respect to a macroscopic observable, such a class that we call now a macrostate. So this is now the precise meaning of a macrostate in the classical picture. And what are these observables, or what could these observables be? So essentially, for example, indicator functions. So we have the phase space here. We identify, we give two different microstates here, and now we evaluate these microstates according to a macroscopic observable, which is simply the indicator function for some subset of phase space. That means, of course, the value of an indicator function evaluated in x0 if x does not belong to a set S, and 1 if x belongs to S. And now you see such functions that assume only the values 0 and 1 have the property of idempotence. They are projectors. And if you remember, I have already said, in C-star algebras, we usually find only a very, very small number of projectors. Now, this is completely different in W-star algebras. In W-star algebras, you can identify a lot of projectors. And this gives rise to the possibility that for W-star algebras, we can consider the corresponding projector lattices that I have explained in the very beginning of this course. W-star algebras can be studied by means of their corresponding projector lattices. So, and this means now that these two microstates are not distinguishable by measuring. Well, so in that sense, a macrostate is an equivalence class of microstates that cannot be distinguished by means of a macroscopic observable. This was my main point here. And yeah.
Sorry. But you only have macroscopic observables?
No.
I'm not fully clear how this relates to the context. if I now say look at the phase space of some harmonic oscillator, so where I cannot have a single location in phase space as a state. So let's say pure states are the ones satisfying the Heisenberg relation. So I have some minimal variance Gaussian function describing my states. How can I connect these two pictures?
Well, the macro states, which will turn out as the macro states in the quantum picture, I come to this point a bit later. But they are not very related to the pure states. They are more related to the density matrices.
Yes, but I would assume that the microstates are related to the pure states.
Well, in a purely quantum physics, in a purely quantum systems, you don't have microstates. Okay. Now I'm only talking about classical systems.
Okay.
Right? And I come back to the issue of quantum systems a bit later, but because it's much more intuitive to consider the classical systems within this framework first. And so I think that was my idea, to explain these notions first by means of classical systems, and then we can make another attempt to understand quantum systems.
Okay.
Yeah. Okay. So again, we are only talking about classical systems here. So we have a system with a phase space. We identify single points in phase space as microstates. We prescribe such indicator functions, for example, as macroscopic observables, namely, of course, these functions are not continuous, right? These are step functions. So they do not belong to the original C-star algebra of continuous functions. They belong to the W-star algebra of essentially bounded functions. But of course, maybe this was your point, the W-star algebra still contains all the intrinsic observables of the C-star algebra, but it's much larger. That's the difference. Okay, wait. And so these macroscopic observables do not allow to distinguish between microscopic states and the phase space, and therefore they become macroscopically equivalent. And here's one of our examples. So, for example, Amari has suggested a macroscopic observable for a neural network, which is given by the mean activation level of all the neurons in the neural network, something similar. So Serafim and I have worked on this issue as well. We are talking about biophysical observation models for neural networks. And one can also look, for example, for an observation model as a macroscopic observable of the fMRI signal. And then one can do further analysis. So, for example, trying to make a segmentation of the fMRI signal into what is called metastable states. And this was one of our last common endeavors here. And this gives us, so to say, a partition of the state space of a neural system into macrostates, namely by means of a macroscopic observable. Well, and again, the algorithm that we have exploited for the segmentation here is based on the idea that there should be some recurrence structures going on in the signal here, and we were able to identify these metastable states as macrostates by means of kind of data analysis that we call the recurrence structure analysis. I come back to this also a little bit later again. So, and that is essentially the point, that macroscopic observables define an equivalence relation over phase space for the classical systems, first of all. And now we can do something similar like the spectral decomposition of an observable, namely by taking linear combinations of indicator functions. And then you don't have a function that is only 0 or 1. It's not a projector anymore. But of course, now we can compute these linear combinations of projectors very much in the same sense as the spectral decomposition in the quantum system. And this gives rise to step functions. So in the literature, you find sometimes the notion of simple functions. Simple functions correspond to such spectral decompositions. And such a simple function induces a partition of the phase space into equivalence classes, namely everywhere, where over all the domains of these respective indicator functions. So we have one indicator function for this region here, one indicator function for that region, and we multiply the indicator function by some scalar coefficients. We take the sum, and then we get a step function over phase space. And this gives rise to a partition of the phase space. So we talk about the induced partition into macro states by means of this macroscopic observable. And this is now related to our work with what we have shown currently.
One thing.
Yeah.
Then you are choosing a macroscopic observable, and that induces a partition in the phase space.
Yes.
Am I right?
Yeah.
Then, if you are choosing a set of classical observables, with this partition, you are building the thermodynamic phase space, for example. Because the thermodynamic phase space depends on the set you are.
Yeah.
So you choose a family of observables and then you build the thermodynamic phase space. And what is the minimal set?
I come to this example as well a little bit later. I will talk about the so to say thermodynamic phase space as well. Yeah. Okay, when we are talking about partitions, and if we have a kind of underlying dynamics here, then we immediately arrive at the notion of symbolic dynamics. So here we have a very simple system. So symbolic dynamics is sometimes studied by means of piecewise linear maps that are globally nonlinear. So this sawtooth map here describes the Bernoulli map. So we have one branch linear mapping for the interval between 0 and 1/2, and another branch for the interval between 1/2 and 1. And now we can iterate the dynamics here. And in this case here, for example, we get a kind of limit cycle or a periodic orbit. What we can do is simply expressing the states, which are the numbers here in the unit interval. We can express the states as binary numbers, as binary fractions. So here, for example, I can say, takes the state 0, 1, 1 in the binary number system and evaluate this in the decimal system. Of course, it is 1 times 2 to minus 1 plus 1 times 2 to minus 2, which is 0.75 in the decimal system. But now, this binary representation of the states, which are simply the numbers in the unit interval, induces a partition, namely into the so-called most significant digits. So if the most significant digit, this is the coefficient of the first power here in this expansion. If this is 1, we know we are in the upper half interval. If it's 0, we know we are in the lower half interval. And then, interestingly, for this simple kind of dynamical system, we apply the flow map that is given here. And of course, we first have to decide in which branch of the map we are. And then you see here applying the flow map to such a system, to such a state, and its binary representation means simply to shifting this string of bits one place to the left. And so this is called a shift map, and the corresponding dynamics is the shift of full type in this case. And interestingly, we can realize that this binary description here extends to all the non-zero integers. And this is now a nice analogy to the Fock space that we have already observed for the Fermi-organic particle system. Interestingly, these kind of piecewise linear maps led to another point of our own research here over the last years. Giovanni Camantini was a PhD student of Serafin a couple of years ago. We were able to construct a modular neural network, a modular recurrent neural network as a Turing machine or as a language processor. So this relates back to things I have discussed yesterday. And essentially, we only need 2 neurons or 2 units in a layer that we call the machine configuration layer in order to describe the state of a Turing machine. And then, because we have a piecewise linear mapping, we have to decide in which branch of the mapping we are. This is performed by the branch selection layer. And finally, we have this linear transformation layer where the actually branch becomes evaluated. And what we do here is essentially applying a kind of vector symbolic architecture, and that what we have discussed yesterday, but in a one-dimensional representation. And this one-dimensional representation turns out to be simply a Gödel encoding of some symbols that we use for this cognitive task, for example, for this language processing task. Then we prepare randomly distributed initial conditions somewhere in the unit square described by these 2 neurons here. There are 3 possible operations going on regarding the language processor that we employ here. So these are prediction, attachments, and accept operations. And this is essentially the result. So you see, we prepare a set of initial conditions in this partition cell, and then we let the dynamics evolve, namely compute the recurrent activation patterns of the neural network. And this trajectory here of rectangles in the partition unit square can be interpreted straightforwardly as a kind of symbolic process, namely as a kind of language processing here. Okay, so far the classical dynamic systems. But then we still have to discuss quantum systems. And for the case of quantum systems, of course, we consider Hilbert space, first of all, as a C-star algebra with the subset of the space of bounded operators, namely the compact operators over Hilbert space. And then we can see that also these compact operators over Hilbert space can be canonically embedded into a W-star algebra. And now the W-star algebra turns out to be the algebra of the bounded operators over Hilbert space. And the proof for this goes exactly the same line as in the classical case. So for the space of compact operators, so we can compute the dual space. And interestingly now, this is exactly the space containing the density operators. This is the space of normal operators over Hilbert space. And then the bidual of the compact operators are the duals of the trace class operators, and they are essentially then the bounded operators. And so now we see the pre-dual of the algebra of bounded operators is simply the Banach space of the normal statistical operators, of the density operators. Yeah. So all the time, when we talk about the algebra of bounded operators over an Hilbert space, we already were talking about W-star algebras and not simply about C-star algebras. Well, now I have already mentioned the representation theorem relies on the so-called GNS construction, the construction that Gelfer, Neumann, and Siegel have suggested for their proof. And we now see that any abstract C-star algebra R for any such algebra and for a given state, which we now call a context, for reasons that will become clear later, we can construct such a W-star algebra of bounded operators over a Hilbert space, namely by this Gelfer, Neumann, and Siegel construction. How does this work? So here we evaluate the states, or this single state, this context state, over the products of adjoint elements of the algebra and themselves. And we take a subset of the algebra that are all these products here become mapped onto zero. So this is the kernel, so to say, in the algebra that is annihilated by the state. This is called the Gelfand ideal. And then we take the quotient algebra of equivalence classes of the algebra. And on this space, we can define a scalar product, namely the scalar product of the equivalence class corresponding to the observable A and the observable B is given by the adjoint of the class with representative A and the class with representative B, and evaluate it in that way. And then you see, because we have a linear functional, can evaluate this, and there's some, of course, some modulus operation that we need, and then we can identify these equivalence classes with vectors in a Hilbert space. And then we can complete this in the weak norm topology. And so from the algebra, we obtain the Hilbert space by this construction. And then, of course, we define a representation of the algebra acting on the equivalence classes of states in the Hilbert space simply by taking the states that correspond to the equivalence classes of the algebra products here. And eventually, we take the topological closure of that, and this gives rise to our von Neumann algebra, for our W-star algebra. I have an example for the spin system here, but it's quite technical, and maybe we can skip this because I'm also running out of time a little bit. And yeah, shall we just skip to the next important point? What do you think?
Yeah, for me, it's all good, yeah.
I will skip this example, which simply shows how the GNS construction works for the Pauli algebra. But now we still need some other concepts. So we call a W-star algebra a factor if its center contains only multiples of the identity. And of course, we also include the zero element here and the identity element. So if the center of the algebra is given by the multiples of the identity. And of course, I have already presented this example to you when we generate the qubit representation of the spin algebra. We came up with the Pauli matrices, and here there was the matrix representation of this Casimir operator, and here you already see this is just the multiple of the identity, and therefore the corresponding W-star algebra generated by these Pauli matrices is such a factor algebra. Then we have to introduce the notion of a primary state. And this goes now along the GNS construction. We say that a representation pi of C-star algebra, we call such a representation primary if the W-star algebra that is obtained through the GNS construction is such a vector with trivial center. And eventually we say, we call also a state on a C-star algebra primary if it is the context state leading to a primary GNS representation. And now we are able to define also that two states of this folium are called disjoint if they both lead to disjoint GNS representations. And you remember, we have called representations disjoint when they are neither unitarily equivalent nor quasi-equivalent. And this is now the important fact, and this relates to your point, how this relates eventually to thermodynamics, for example. We see that the normal folia of two primary disjoint states have no states in common. And this means that the state space of an algebraic system can be partitioned into these normal folia. And even more, I come back to this issue later, but first of all, we have to look at spatially extended systems that are described by quasi-local algebras once more. So here now consider a quasi-local algebra and such a primary state that leads to a primary GNS construction. And now you remember these quasi-local algebras have this property of locality that observables from disjoint regions in the topological space are commuting with each other. And this gives rise to this important property, and it's called the clustering property. And here you see we are evaluating a product of observables in a state, and then these products here factorize under this assumption. So they can be made arbitrarily small. And the proof for this essentially goes by looking at the fact that spatially separated observables commute eventually with each other. And because we have a primary state for this evaluation here, that generates a W star algebra with trivial center. And therefore, we can see that the evaluation of these states must be a multiple of the identity, and then we can derive this clustering property here. But does this look somewhat familiar to you? Maybe in the framework of thermodynamics and statistical physics also. Something similar appears in the Boltzmann equation, where you are in the collision integral of the Boltzmann equation, you always have these products of probabilities. I have already mentioned that before. That means decorrelation here. So here we have to evaluate joint probability distribution, and is factorized into the product of probability, into the product of probabilities. And this is, according also to the Boltzmann equation, this is, so to say, the source of all the nonlinearities that appear in phenomenological models. And the reason for this is essentially locality. That observables taken from different regions in space commute with each other. Well, now for the quantum framework, we can.
Peter, can I ask you maybe a very stupid and naive question, because I don't know much about quantum. So entanglement doesn't fall into this at all, because
no, it's completely different
outside, right? Because they don't have a notion of space at all.
Yeah, we have a notion of states, and these states could still be entangled,
Yeah.
but it's not related to the locality, which is a property of the observable algebra. And now in this algebraic framework, we can now do the same steps that we have discussed before for the classical systems. We can define these macroscopic observables again for the case of quasi-local C-star algebras. We consider space translations in the automorphism group. We can average over all this spatially translated results of this single observable. We average this over some region in the underlying space. And then we can evaluate these observables in a given state. And if the limits of these functionals exist, then we can eventually assign a macroscopic observable which takes the state as its argument and identify this with this limit of these local averages here. And this defines now a macroscopic observable over the state space. So now we are in the W star algebra, namely in the bidual of the underlying quasi-local C star algebra. And we see if we have a primary state with some normal volume, so the set of all the states that can be generated by modifications, then all the other states that belong to this normal volume, they are macroscopically equivalent with respect to all the macroscopic observables in the W star algebra. This is a quite important property here. And now we see that we also obtain this kind of partitions in the quantum case, in the pure quantum case. So let rho 1 and rho 2 be two disjoint primary states in the volume. And then we evaluate a macroscopic observable of the W star algebra. And this partitions the space of all the normal states into disjoint normal folia. So now we are able to identify these normal folia with the macro states. Normal folia are macro states in the quantum picture. And additionally, when we evaluate macroscopic observables, it appears that these are dispersion-free over macro states. And this gives rise to these thermodynamic observables. Because when an observable is, or when a state is dispersion-free with respect to an observable, it should be a classical state, and then we can generate such a classical phase space picture for thermodynamic variables. That's the point. Interestingly, this picture leads now straightforwardly to a solution of the measurement problem of Ionic quantum theory. One should be a bit careful with this claim. So has shown this already in the 70s, but it's still a little bit debated today because essentially has provided only necessary conditions for the solution of the measurement problem. So there are still some technical problems involved, but how does this work? So here's a very important application. All the states within a volume are macroscopically indistinguishable. So if we have a macroscopic observable, we cannot distinguish the states in a normal volume macroscopically. But now, if we now take the irreversible relaxation dynamics of our measurement devices into account, so here, for example, that the lever of such a scale must have relaxation dynamics into equilibrium, this irreversible relaxation dynamics leads to what is called asymptotically disjoint states. And for asymptotically disjoint states, we get different results from a macroscopic observable. So these become macroscopically distinct and therefore macroscopically distinguishable. And we can finally read out the macroscopic observable. So there is no measurement problem. In pioneer quantum mechanics, of course, we had this pertinent measurement problem, and that was ad hoc, so to say, solved by von Neumann's projection postulate. And here in the algebraic framework, there is no measurement problem at all. Being a bit more careful, of course, maybe there's still some work to be carried out about it. But in principle, we see that we get these asymptotically disjoint states here. So, and then we can discuss W star dynamical systems, which are, of course, quantum dynamical systems. Now with the W star algebra, the state space is a normal volume, and the representation of the group representation of the automorphisms is weakly continuous in the algebra. And here is another example from our most recent publication by Markus Huber-Liebel and the other colleagues from Cottbus University. And this works as follows. So we call these quantum-inspired cognitive agents. So in one example that is standardly considered here is a cognitive agent. So for example, a mouse running through a maze. So this is a classical mouse maze problem. And classically, the behavior of this agent is described in a perception action circle. And actions must be made by actuators, by motors, for example. In a quantum frame, we simply describe a C-star algebra, namely operators or actors. And of course, here you see, so everything seems to work again. Well, so we consider a cognitive agent in a maze, for example, and of course, the agent is able to measure its own position. So this corresponds to a position, to an eigenvalue equation for the position operator. And essentially, that there should be some target in the maze. So the mouse should be able to find a piece of cheese. And then, of course, it should be able to detect the presence of cheese. And so there is another eigenvalue equation that the cheese operator or cheese perceptor applied to a position state should be either no cheese or the presence of cheese at this place. And then you see this is an eigenvalue equation with only eigenvalues 0 and 1. So cheese should be a projector in that case. And then, of course, there are these action operators that the mouse should be able to go one place to the left or one place to the right or to the up or down. And this is expressed by these action operators, which turn out to be related, interestingly, to the ladder operators in the spin algebra. And eventually now we have a kind of dynamics in the system where the observables become updated during exploration of the maze. So that means we start with the 0 operator assigned to the position measurement at time 0. So t is here the time index now. And then at any instance of time, we have an already updated position operator, xt. And then we look, we make a position measurement in the state x. So we compute the observation, we compute the expectation value of the observable xt in the state x. And if this is 0, we have this entry here. So this gives us the possibility to make an update of the state. And this means that we have to extend the already learned position operator simply by a new entry, which is a part of the spectral decomposition. And in that sense, by means of this dynamics, you see we are learning the spectral decomposition of those operators. And this has been
backward, sorry.
What?
You said backward what?
What?
I did not understand the last sentence. You're learning with what, sorry?
This spectral decomposition.
Ah, yeah, okay, yeah. So yes, okay. Now I got it. Yeah.
No. No, if you iterate this algorithm here over time, then you get immediately a linear combination of eigenvalues times projectors, and then you see that the operators are iteratively updated towards the spectral decomposition of those operators. And this has been elaborated by Markus Huber-Liebel here. And the result of that is now that this learning algorithm can be used for the inference of ontologies. So we can relate this back to the very beginning of this course. So here the agent is able to explore the maze, and here there are 3 cups of water, and only in one place there is a piece of cheese. And here we have a state where the mouse has already explored the first place here, the second place in X direction, the third place in X direction, and the second place in Y direction. So we are here. And so by the iterative construction of these operators, we can describe the logical structure by means of these Hesse diagrams, and they represent the ontology that had been learned in a particular point in time. And then we make a transition. So from this place, another exploration step leads us to this place. Here you see a new projector appears here, and these projectors together can be combined by the spectral theorem in order to get the values of these observables standing for cheese and a glass of water. So in that sense, we can now describe the emergence of an ontology, namely by a W-star dynamical system. So, okay. Now again, for something different, and this is really the last topic that I would like to address in this course. We have to consider stability. And one important property of stability is called stationarity. And now again, we look at the W-star dynamical system with the W-star algebra, volume as a state space, and an automorphism group or a representation of an automorphism group. And now we call a state in the volume stationary if it does not change over time. And of course, from classical dynamical systems, you certainly know that the states will be called stationary when all the statistical moments do not change over time. And this now directly relates to our states as interpreted as expectation value functionals. And so here we have an original observable, and here we have time translate. So the observable at another time t, and if we evaluate the state, it's the initial state for all observables. And this applies, of course, again to our thermodynamic system. So here, for example, to the Gibbs state, and it's straightforward to show that these Gibbs states here are stationary states describing thermodynamic systems. This slide I just repeat again in order to show you that in nonlinear classical dynamical systems, we are able to identify these scenario-Bowen measures. And these measures have exactly these 3 important properties. They are stationary, so expectation values and probabilities do not change over time. They are structurally stable, or what I like to call resilience now. So that means a slight perturbation of the flow of the dynamics in parameter space leads to essentially the same behavior. So this is mediated by a continuous transformation. They are topologically, what's the word? Conjugated. They are topologically conjugated. And then finally, you have a similar property like the clustering property I have shown before, which was about the loss of spatial correlations, but now it's also important that you have this loss of temporal correlations, and this is called the mixing property. So this is very well known for classical dynamical systems, for chaotic attractors, for example, but now we can try to import or to export these notions to the algebraic framework. And this has been done by 3 important researchers, by then correspondingly such a state is called a KMS state if it allows the introduction of such a parameter, the inverse temperature, and if the state is first of all stationary, and if this condition here, the so-called KMS condition, holds. And here you see that we evaluate a state for the time involved observable A and another observable B, and this should be the same as the state evaluated at B, and then here we have to make a kind of gauge transformation in the automorphisms, applying this to A. This is the so-called KMS condition, and this condition holds naturally for Gibbs states. So here again, because the Gibbs states are used for the derivation of this KMS condition, and so Gibbs states are naturally KMS states. But now, interestingly, Haag has shown also already in the 70s that these KMS conditions can be further deduced, namely exactly from these 3 important criteria of stability. Of course, first of all, we have to assume stationarity in order to talk about a KMS state. But then we see that a slight perturbation of the state does not change the system as long as the slight perturbation still belongs to the volume generated from the state by local modifications. And additionally, Haag was able to derive this mixing property from a purely algebraic constraint that is called asymptotic abelianness. And also for this case, one can show that the states evaluated at macroscopic observables, or vice versa, macroscopic observables evaluated at those states are dispersion free. And so they have exactly properties of classical thermodynamic properties again. So these are the KMS states. And interestingly, it was possible to apply or to employ the same procedure to some C-star dynamical systems, namely essentially to Markov chains. And so it was possible, for example, to devise a C-star dynamical system for the Bernoulli shift. This leads to the so-called Kunz algebras, and it was also able to develop the same approach for so-called shifts of finite type. They are called Kunz-Krieger algebras. So these are the C-star algebras describing these kind of Markov processes or Markov chains. And eventually Harald Atmansbacher and I have recently shown some years ago that again you can relate the KMS properties of these Markov chains with exactly the same kinds of stability, namely that the Markov chain must be described by a transition matrix, by the transition probabilities from one macro state to another macro state, that there's the existence of an eigenvector for eigenvalue 1, which is simply the stationary distribution of the Markov chains. Then under some assumptions, according the corresponding partition that gives rise to the Markov chain, we have something similar that can be called resilience. Namely, one speaks about Markov partitions. And finally, we have argued that if the Markov process is ergodic, that means that the transition matrix is irreducible, then we already have this mixing property as well. And this was quite a nice finding, which we could further employ again now in neuroscience. What I have mentioned before, this approach for segmentating time series into metastable states can be described by one particular transition matrix. And here the idea is that the transition matrix must have a particular shape. Namely, in order to speak about metastability, we claim that the transition from one state to another should be, of course, there should be a certain probability for such transition, but the highest probabilities are that there are transitions from one state to itself. This is our criteria for metastability, and so we are able to say that the transition matrix should approximately such a shape, and for such a transition matrix, we can write down a kind of utility function, and maximizing this utility function gives rise to the segmentation of time series into these metastable states by the properties of such a maximally stable Markov chain. So and now I'm already at the end, and I will talk about a more philosophical issue, if you like. We have already seen when we were talking about this GNS construction. The GNS construction relies on the selection of one particular state that we have called a context state. Now we can show that everything crucially depends on this context state. And in fact, particularly for quantum systems with an infinite number of degrees of freedom, it can be shown that different selections of context states lead to disjoint representations. What we have seen for the case of this quantum spin chain, for example, that such disjoint representations, representations that are not unitarily equivalent to each other, are crucially dependent on a suitable or appropriately chosen context. And I would like to illustrate this idea of contextual emergence. So here, again, let us look at a C-star algebra and a state that we call a context state. And then, of course, by means of this GNS construction, we can construct a corresponding W-star algebra. This is induced by the state. And we say that this W-star algebra is contextually emergent if the chosen context state now really satisfy several stability conditions. And these stability conditions are always related in one or the other way to the KMS conditions we have considered for the emergence of thermal equilibrium. And now the weak topology induced by this particular context state, this, so to say, specifies what we consider as being relevant for our construction. So in that sense, our values of relevance come into the construction of disjoint representations. And here is a nice illustration from Gestalt psychology. So clearly, you interpret this middle symbol as a B, right? But now I change the context. What do you see now? So in that sense, one can speak about contextual emergence. And for that, I also have few examples. First of all, this is again thermodynamics. Namely, The W star algebra of thermodynamic observables contains, for example, temperature, pressure, chemical potential. This is contextual emergent from the selection of these particularly selected maximally stable KMS states. And in that sense, KMS states express the notion of thermal equilibrium. And the thermal equilibrium is not present at the level of the ontological level of the C star algebra. So in other words, if you do statistical mechanics, you do not have a concept of thermal equilibrium. You have to add your assumption of thermal equilibrium in order to be able to derive thermodynamics out of statistical mechanics. So eventually, these KMS states give rise to the usually classical observables in thermodynamics and correspondingly to the dispersion-free thermodynamic microstates, which give rise to the thermodynamic phase space. Well, here's another illustration of the basic idea of contextual emergence, that complex systems can be described at different levels of abstraction, so to say. So always we have to speak about a lower level, and then we have a higher level, and contextual emergence applies to the case that the lower level only prescribes necessary conditions for the higher level description. So necessary conditions mean that the higher level implies the description at the lower level, but not vice versa. But now if we embed our lower level description into a particular context, which is implemented by means of stability criteria, then we also add the sufficient conditions, and then we have both conditions together, necessary and sufficient conditions, in order to describe systems at a higher level of description. And here's one important application, namely the emergence of molecular structure. So here you see an example of a very, very complicated macroscopic molecule. But first of all, you would describe such a molecule as a quantum system by means of a Schrödinger equation. But if you try to do this, first of all, of course, you cannot solve the Schrödinger equation analytically as any other many-body system. You have to use some perturbation methods, and also, even more important, that this molecule will be in a highly entangled state, and one cannot say it has a spatial structure at all. What is done here? One uses singular perturbation theory. And usually it's called the Born-Oppenheimer approximation. So historically, Born and Oppenheimer presented a kind of perturbation series expansion, but later it became clear it is not an approximation at all. It is basically an example for singular perturbation theory. What does this mean? Well, one introduces a perturbation parameter for a series expansion, which is given by the square root of the electron mass over the nucleonic mass. And then you assume that the nucleonic mass tends to infinity, and therefore this perturbation parameter goes to 0. What does this mean? When the nucleonic mass goes to infinity, that means essentially there's a rigid nucleonic frame. And for that rigid nucleonic frame, you can solve the electronic Schrödinger equation alone. And then you close the loop, so to say, and assume that the nucleonic frame is determined by the minimum of the electronic distribution of the electrons over the molecule. And of course, this assumption here leads to a separation of time series. You assume that the nucleons move much slower than the electrons. Electrons can immediately adapt to any change of the nucleonic frame, but the nucleons have a different time scale, and this is expressed by the singular perturbation theory. But the example I have shown before was just an example for an ion channel. It was the potassium channel in the cell membrane. And here we have another stage, so to say, of contextual emergence, namely the functioning of such a molecule as an ion channel. And this leads now to the description of as a Markov chain. So the nucleonic frame determines the spatial structure of the molecule, and of course, therefore, also whether there is an open or a closed pore. But by means of this perturbation theory, it becomes a stochastic dynamic system. And such a stochastic dynamic system can now be approximated by a Markov chain, and then you know there is this transition matrix, and the ion channel is then essentially described by the state of an open pore, the state of a closed pore, and some transition states. And we can use the same formalism as we have done for the detection of metastable states, for example, in order to describe the emergent properties of the molecule, namely its functioning as an ion channel, as an open or a closed pore. Well, this is my last example, but perhaps I shall skip this if you like. And let me just come to my conclusion. So first of all, we can discuss this if you like it later. So eventually you remember that I have introduced C-star algebras as the ontological structures, so the descriptions of ontological structures. But now we are able to also talk about the W-star algebras, namely in the sense of contextually emergent properties. And these, of course, provide the epistemic descriptions of a system under the perspective of what is being considered relevant for a specific investigation. So this would be my last claim, that the C-star algebras the C-star algebras reflect the ontology, and the W-star algebras reflect epistemology. So this is now my final conclusion, that algebraic quantum theory, of course, it does not provide a theory of everything or the grand unified theory or so, something like that. This is not the case. But in fact, it provides a universal abstract language for describing all these different kinds of systems. It does not depend on specific frames of reference, so it does not depend on coordinates that are usually selected in a Hilbert space description. It does not refer either to specific context, so it is also representation independent, unless one needs a representation for a particular application. And as I said, it distinguishes uniquely between ontological and epistemic descriptions. Ontology refers to the structure of the system as it is, and epistemology refers to the meaning of the system insofar as it is relevant for an observer. And some further properties, of course, they are generally scalable and universally portable. And that's the conclusion of my lecture.
I have a question with that.
Yeah.
So these stability conditions
Yeah.
would not work for instance, non-autonomous systems, right? So you'd so how do you define the stability conditions when you have, say,
well, in principle, an open system is a non-autonomous system.
is
a non-autonomous system.
correct?
So it works, of course, it does.
So you can always find stability conditions for a non-autonomous system.
Yes.
So you can always find.
This is the idea. Of course, we have to embed our non-autonomous system into an environment in order to create a kind of autonomous system, and then we divide the system again into the open system that is really public real environment. And another example was this quantum-inspired agent. So the mouse moving and exploring a maze. Well, of course, the mouse itself could be seen as an autonomic system, but if some experimentator manipulates the shape of the maze, it would be a non-autonomic system. But I think it's still forward to make this.
Could I ask also that because of your time series analysis, the brain data, and the brain is completely open.
Yeah, sure.
Right. And so, but you still have conditions to derive your partition.
Yeah.
Your Markov partition.
Yeah.
And so it is the case that you can very high dimensional system where it's completely, say, weakly coupled to its environment.
Yeah. Right.
And then you have these conditions for partitions.
Or another example is what does it mean to have a stochastic system? And essentially, the basic assumption of a stochastic system is a system with an infinite number of degrees of freedom. And this comes from coupling some system weakly to the environment, so in principle to the entire universe, such that the entire universe can have an impact on the degrees of freedom of the system. And so stochasticity is always a kind of non-autonomous system in that sense. And of course, this algebraic approach that is perfectly suited for the description of stochastic systems as well.
But in a sense, also this, I don't know how to interpret this, but in a sense, the detailed microscopic dynamics of the brain we will never know, so to speak.
Clearly not. And therefore, it is important to become aware about the relevant context.
So only our context can describe,
so to say,
but
yes.
the details of the brain we will never know.
This is really the crucial point, the most important gain of knowledge, so to say, that has evolved during the development of this algebraic approach, that for systems, in the case of an infinite number of degrees of freedom, we have these disjoint representations. And these disjoint representations cannot be uniquely unified into one and the same picture. And we have to impose context in order to decide what kind of representations we are really interested in.
Right.
And so in the beginning of the class, I said something about perspectivity when we were discussing these Boolean blocks in a non-Boolean lattice structure. So perspectivity means, so to say, the freedom of choice to decide for one relevant perspective. And even more crucial, the same holds for contextual emergence in order to make a selection between these disjoint representations.
I have a last question before the others ask. Sorry. In this W star dynamical system framework, it's a triplet. Where does the Koopman or operator, or its adjoint, the Perron is operator sit? I mean, where is? How do I place it there?
Yeah, this is essentially nothing else than the states that we have introduced for classical dynamic systems.
Oh, these are the states.
Yeah, these are the states. They are related to the states.
Because the Koopman operator essentially iterates the observables,
right,
so to speak. But it's not really related to the state, right?
No, it is. Because when we go back to the slides. So here we are. You are introducing these probability density functions, and then you are evaluating these integrals. So this is essentially the expectation value of the observable x. Is the density as the weights, and this gives the expectation value of the observable x. And of course, in the C-star algebraic system first, we make the observables time dependent. But of course, you can also make the states time dependent, the same as it's done in quantum physics between the Schrödinger and the Heisenberg picture. But then if we apply the temporal development to the probability density functions, we have to use the Frobenius-Taron operator. And that's the description. That's it. And the only difference then is, of course, that you are able in the von Neumann-Koopman representation to introduce also Hilbert space, where all these operators act upon. Right. That's not a difference. But essentially, it's just this here.